Advanced Algebra 2, using properties of rational exponents and radicals. And now we're going to use these properties to add and subtract like radicals and roots. I do not have a note sheet for this, so you'll need to have some notebook paper and write down these examples. Note the example number because they come right from the book, from chapter 5, section 2. That way, if you want to look back into the book for some more support information, you can do that. Radical expressions with the same index, remember that's the root, and radicand, that's the number underneath, are called like radicals. So to add or subtract radicals, they need to be alike. So in example 5, A, we've got the fourth root of 10, and there's one of them, so there's just an understood 1 in front of that problem, plus 7 fourth roots of 10. So let's get there. Now, if your radical is the same, so fourth roots of 10, you can add them. So we have 1 fourth root of 10 plus 7 fourth roots of 10 will give us 8 fourth roots of 10. It's like adding variables, okay? They have to be the same. Now B, even though it's not in radical form, it's in rational exponent form, it works the same way. So we have 2 8 to the 1/5 plus 10 8 to the 1/5. That will give us 12 8 to the 1/5. And let's just be consistent and rewrite that in radical form. So remember, the bottom number of the exponent is the root, the base is the radicand, and then to the first power. So we have 12 fifth roots of 8. Now C, we have the third root of 54 minus the third root of 2. Our roots have to be the same in order for us to combine them. So we can't force them to be the same, but we can break down the third root of 54. So I know that, let's see if 8 divides into 54. It does not. So we have 9 and 6. And neither of those are perfect cube roots. So I'm just going to come over here and write factors of 54. So we've got 2, aha. I just couldn't think of it right away. But 2 and 27. 2 is a perfect, 27 is a perfect cube root. So now I can take the cube root of 27, which is 3. I'm left with the cube root of 2. And then I'll finish my problem. Okay, now the cube root of 54 has simplified into 3 cube roots of 2. I can subtract that 1 cube root of 2, and I'm left with 2 cube roots of 2. So again, I can't force the roots to be the same. I just simplify, and if they end up being the same here, then I can go ahead and complete that adding or subtracting. Alright, so write down the next one. We have 7 fifth roots of 12 minus 1 fifth root of 12. I always read it like that to help me actually see what's going on. So that will leave us with 6 fifth roots of 12. Now here we've got 4 9 to the 2/3 plus 8 9 to the 2/3. So again, we can write that as 12. 9 to the 2/3. And we can rewrite that, so we've got the cube root of 9. I can't simplify that because 9 is not an even cube root, but I just rewrite it to check and see if I can. Alright, now number 12, write this one down. We've got the cube root of 5 plus the cube root of 40. I can't add those roots because they're not the same, but I can break down 40. I know that 8 will divide into it. 8's a perfect cube. Ooh, and that works out perfectly because I'll be left with the cube root of 5. So the cube root of 8 is 2 cube roots of 5. So now I have 1 cube root of 5 plus 2 cube roots of 5, and that leaves me with 3 cube roots of 5. All right. Now sometimes we're just asked to simplify expressions. And now notice we have variables in these expressions. So this is example 6 from chapter 5, section 2. So write down A. We've got the cube root of 64 and then y to the 6th. So we take it one piece at a time. So first look at the number, and we're going to take the cube root of 64 if we can. And 64 is a perfect cube. It's 4. So once we take that perfect cube, it comes out. Now we've got the cube root of y to the 6th. So that's asking how many groups of 3 y's are there in y to the 6th? Well, there's 2 groups of 3 with none left over. So this is the cube root of 64y to the 6th. It's 4y squared. If I were to multiply these guys together 3 times, I should get what's underneath that radical. So 4 times 4 times 4 is 64. Y squared times y squared times y squared is y to the 6th. So that checks. Now write down the next problem. We've got the 4th root of x to the 4th divided by y to the 8th. Remember the properties of radicals that we can rewrite that as the 4th root of x to the 4th divided by the 4th root of y to the 8th. So the 4th root of x to the 4th is simply x. You can think of it as how many groups of 4x's are there in x to the 4th? Well, there's just one, x to the 1st. How many groups of 4y's are there in y to the 8th? Well, there are 2, with none left. So that's how we can simplify those. Let's try a few more. So these are from example 7, if you want to write that down. And A is the 5th root of 4, A to the 8th, B to the 14th, C to the 5th. So we, first of all, look at 4. It's not an even 5th root in 4 or in any of its factors. So now we look to A to the 8th power. How many groups of 5 or 5th root of 5 a's are there in a to the 8th? Well, there's 1 with 3 left when we take out that one group of 5. How many groups of 5 b's are there in b to the 14th? Well, there are 2 with 4 left over. It's like dividing. And then how many groups of 5 c's are there in c to the 5th? Well, there is 1 with none left over. So this is our final answer, ab squared c times the 5th root of 4, a to the 3rd, b to the 4th. All right, so now we have x over the 3rd root of y to the 8th. So first of all, let's just deal with the denominator. So how many groups of 3y's are there in y to the 8th? Well, there are 2 with 2 left. Now we need to rationalize, so we're going to multiply top and bottom by the same root, same base, but the power that when we add them up, they will equal 3. So we'll have the 3rd root, x times the 3rd root of y, and then we'll just bring our y squared. And then when we multiply these guys together, we get the 3rd root of y to the 3rd power, which is simply y. So we'll end up with x times the 3rd root of y all over y cubed. Now lastly, we've got 14xy to the 1/3 power over 2x to the 3/4 power and z to the -6. So let's start with our numbers. 14 divided by 2. We can think of that as a fraction. We're just going to reduce it, so 7. And then with our x's, we're going to subtract the powers. So bigger minus the smallest power. So 1 minus 3/4. Our y, we don't have anything to combine our y's to the 1/3 with. And then our z to the -6, we're just going to move that up top and make that power positive. I am not left with anything but just a factor of 1 down below. So that denominator is, we can just leave that off. So now I've got 1 minus 3/4, which is 1/4, and then times y to the 1/3 times z to the 6th. And that's all I can do. I can't put them under the same, change them into radical form because my roots are different. So I just leave them in exponent form. And usually the way we do it is if the problem starts in radical form, like a and b, you're going to give your answer in radical form. If the problem started in exponent form, then we'll leave it in exponent form. All right, lastly, we're going to add and subtract variable expressions. So this is example 8 from chapter 5, section 2. You can write down A. So we have 5 times the square root of y plus 6 square roots of y. So notice that the radicals are the same. And in that case, we can just simply add them. So that gives us 11 square roots of y. We don't know what y is, so we can't take the problem any further, but we can simplify that way. So now b, write this one down, 12 cube roots of 2z to the 5th minus z cube roots of 54z squared. Okay, so we can't combine those right now because our expressions are not the same. But let's see what simplifying we can do. So first I'm going to look at my first expression. Cube root of 2, that's as simple as I can get it. But the cube root of z to the 5th, I can take out one group of 3 z's. And then I would be left with that 2 and then 2 here underneath when I take out that one group of 3. So essentially it's like 5 divided by 3 goes once with 2 left. All right, now my second expression, cube root of 54, so I know that I can break that into 27 and 2. So the cube root of 27 is 3. And then I will have that cube root of 2 left. Oh, this is looking promising. Oh, and then I have a z squared underneath. And let's see, do I have a z? Yes, and that z front. All right, now I'm going to look and see if my variable expression is exactly the same. So I have 12z cube roots of 2z squared and 3z cube roots of 2z squared. So since all of this is identical, we can take those 12 and subtract those 3. So that will leave us with 9z cube roots of 2z squareds. All right, so that concludes the notes on using properties of rational exponents and radicals to add and subtract expressions in section 5.2.